Okay, so this is Pascal's triangle. It's a triangle, right? Looks kind of like a Christmas tree if we put the little trunk there. And this triangle shows us quite a few things. One special characteristic about this triangle is that each number is the sum of the two numbers to the right or left, if you go above. And it basically represents the number of ways to get to a certain position using down and right or down and left movements. Another thing is the rows are counted 0, 1, 2, 3, 4, 5, 6. And let's say for this position here, we're going down and right, and then down and left, or we're going down, left, or down right, which we actually can't do. Notice that's why this 1 isn't added when we're counting how many possible ways. It's just the ones above it, like directly above it. So we'd actually be going down left, down right. You could see both of these possible paths. Actually, there's more than one. There's down left, down right. There's down right, down left, down right, or down right, and then down left over here. Kind of difficult to trace. There's that. There is that, and then there is that, which gives us a total of 3 paths. Another way we could calculate this without having to draw all these paths or write out the entire triangle, we could take whatever row we're on and we could do 3, choose, because we're choosing 2 times going to the right. So we're going to the right once here, once here, or we're going here and here. 3 choose 2, which will equal 3. Notice that 3 choose 1 also equals 3, because if we were only choosing 1 time that we're going to the right, it would actually end up here, which also equals 3. And if you're wondering how to calculate this notation, these are called binomials. Okay, so let's say we have 4, choose 2. We'd expand it to 4 times 3 times 2 times 1. And the bottom part is always going to be 2, or whatever number is here, and then 4 minus 2, and then we have this exclamation mark. What the exclamation mark means is 2 times 1. Here it's also 2 times 1. Up here it's 4 times 3 times 2 times 1. Let's cross that out. The exclamation mark pretty much means, like, let's say we had 5 exclamation mark. It's 5 factorial. 5 times 4 times 3 times 2 times 1, and until you reach 1. And this gives us, this will cancel out this, and this is a 2, so we get 6. So if we wanted to choose 2 times we're going to the right, then we'd get this. That's how many ways there is to get to that one point. Binomial theorem actually has quite a few applications, which we'll see in later slides, and there's a few formulas, but I believe that if you understand the conceptual ideas, you don't really need to memorize formulas as much, because it can be a little messy and difficult to memorize. So these are the formulas I was talking about. We have the binomial theorem expansion, which I'll cover in the next slide, and we also have the rth term of the expansion. It involves this binomial notation, which I showed you how to calculate, and it basically stems from the Pascal triangle, which I'll show you again in the next slide. But as you can see, these are not fun formulas to memorize. Even I don't have it to memorize, but I understand if you were to give me this and ask me what the rth term is, I would technically be able to do it. I just would not be able to use notation because I find it quite difficult to memorize. So here, this is our binomial expansion using the binomial theorem. There's actually some confusion for me. This is a binomial because it has 2 terms, right? But binomial theorem is a completely different thing that can be applied and used, somewhat related. Anyway, so we're expanding this. It's x plus 1, x plus 1, x plus 1, x plus 1, multiplied 4 times. And of course, FOIL, so of course you could multiply it out all manually, but that is not very efficient. Instead, we're going to look at our wonderful pal, the Pascal triangle, again. And so because we're raising it to the fourth power, you could notice that if we were raising x plus 1 to the 0th power, it would just be 1. If we were raising x plus 1 to the 2nd power, you probably know this one already, it'd be 1x squared plus 2x plus 1. And you could see this follows a pattern. So this is the 0th row, this is the 1st row, this is the 2nd row, this is the 3rd row, this is the 4th row, and it corresponds to whatever power you're raising it to. So we're going to use these coefficients here, these 5, and we'll have 1 x to the 4th power plus 4x to the 3rd power plus 6x to the 2nd power plus 4x plus 1. And wow, we've just saved ourselves a ton of work by using Pascal's triangle. But if you do want to understand why this is happening, think of it as our left, and down, right movements. We can consider choosing 1 when we're multiplying as a down right movement and x when we're multiplying as a down left movement. If we were to choose as many x's as we were 1's, we're going to be choosing down right twice and down left twice. And let's say we start here. Let me change my color. We're going to be going down right, down left, and we end up at 6. And any possible combination you have, you're still going to end up at this 6. And there's 6 total paths to it, which means when we multiply it all out with every combination of where we have 2 x's and 2 1's, when we multiply this out, we get 6 x squareds. And likewise, if you were to only choose x's, as in only go left or only go right, there's only one possible outcome you could have. Here it's 1x to the 4th and 1, because it'd be x times x times x times x. It's not FOIL because you're using a different method. You're just counting all the possible ways to maybe get x to the 3rd power, or x, which is the same because instead of choosing only 1x and 3 1's, you're choosing only 1 1 and 3 x's. Because there's no coefficient, everything is the same. But if you had something like x plus 2 to the 4th power, it will not be the exact same coefficients as you find in your Pascal triangle, but rather you would multiply it by some factor that you would determine by the binomial theorem, as we'll see in the next slide. Okay, so like I told you before, we are going to have a example where the coefficients aren't just 1, meaning it's slightly more difficult, but it's still possible. So in the expansion of a binomial, terms are written from highest degree, which will in this case be x to the 7th power, to lowest degree, which is of course x to the 0th power, because we have a term with x to the 0th power. And we want the second to last term, which means our second to last term has 1x to the 1st power. So we're going to find all the ways that when we expand this, we only use 1x, so we only multiply it by a 1x term. And using our binomial notation, or our choose notation, we're going to find the number of ways to choose 1x out of 7 of them, because we're multiplying this binomial with itself 7 times, because we're raising it to the 7th power. So 7 choose 1, and the 2x has the coefficient of 2, so we're multiplying that 1 time. The 4, negative 4, will be multiplied 6 times, because it has to be 7 times in total, so 1 plus 6 is 7. And we have our x of 1 degree, which becomes 7 times 2 times negative 4 to the 6th power times x. I'm going to change colors real quick here because this is very bright. And whatever 4 to the 6th power is, give me a sec here. Okay, that's big. So 57,344 x will be the coefficient, well, of the term, and this is our second to last term in the expansion. It's not very difficult. You just have to think about it and do this calculation. In fact, when you have to expand the entire binomial instead of just finding a singular term, that can get quite annoying because you have 7 terms, but it's doable. Here, this isn't much of a binomial theorem question as much as it is of just a regular binomial. We're finding the number of ways to arrange 4 1-hour study blocks in a 10-hour day. We can think of this as we have 10 blocks, right? And we want to choose which 4 of them we're going to paint the wonderful color of red because studying is painfully killing. So let's have our 10 boxes. Let's see if I can actually count 10 boxes out. 1, 2, 3, 4, 5, yeah, okay. So we want to find the number of ways to paint 4 of these red. We could do 1, 2, 3, 4, or we could do 1, 2, 3, 4. There's a bunch of ways, and there's no way we're going to be able to count it in an efficient way without using some sort of formula. So we're basically doing 10, choose 4. I actually messed up my interpretation over there. 10, 4. It's not a fraction, it's a binomial. And what this actually represents is there's 10 factorial ways to arrange every box, right? And we want to find the number of ways to arrange 4 of these so that we know which 4 are going to be our study blocks. So we do 4, and the other 6 blocks also have to be arranged. And like this is our 10 choose 4, which is just 10 times, okay, I messed that up. 10 times 9 times 8 times 7 times 6 and so on, right? One way we can shorten this calculation is just doing 10 times 9 times 8 times 6. I cannot count downwards today. 10 times 9 times 8 times 7, and because we only have 4, we'll just do 4 times 3 times 2 times 1, because if you notice the 6 factorial and the remaining 6 multiplying things that we're multiplying by, we'll just cancel out. And here we have 4 times 2 equals 8, we can cancel that out. This becomes 3, 30 times 7, so there's 210 ways to calculate how to arrange 4 1-hour study blocks in a 10-hour day. See, one wonderful way to procrastinate on your work is to calculate the number of ways you can do something rather than doing something. So there's a counting method where we can count the number of arrangements like this, and it's called stars and bars. No, I'm not talking about the Confederate flag. It might seem similar, it's not at all. So we have 6 cars and 3 people, and we want to find the number of ways to arrange this, and because just life is unequal, so they're not just going to split it 2, 2, 2. One person wants 4 cars maybe, and the other will only get 1. Don't know yet. So we're going to have our cars. I'm going to color them red. And our people are going to be blue. Okay, this looks an awful like a flag now. Okay, so we're going to be arranging these, and one way to count this is like dividers. So these 3 people are going to be the sort of bars. Let's put them like this, and we'll fill the rest of it like this. And we're going to have 1 bar always here, which will just collect whatever is remaining. So it's going to be the complete rightmost bar. So this guy, let's call him guy number 1, is going to get 1 car. Let me change colors. This guy is going to get 3 cars. This guy is going to get 2 cars. So another way we can look at this problem is the number of ways to arrange these bars, which will give us the number of ways to divide these cars, these 6 cars. And we can look to our previous problem where we're dividing the number of hours in a day and create boxes. But like I said before, this one guy is going to always be at the rightmost. He might not get any cars. He's just going to be there to make sure all the cars are distributed. And we will have, let's see how many this is, 8. So we have 3 people plus 6 cars minus that 1 person who's just going to be out on the right to make sure we don't have any cars left over. And we're choosing how many dividers. We have 3 minus 1 divider because we have 3 people and one person is just on the right, making sure all the cars get taken. And it becomes 8, choose 2. 8 times 7 divided by 2, 28 ways to divide these 6 cars. And if we were to, let's say, make sure every person got at least 1 car, we could just subtract these 6 minus 3, and let's say we start out with 3 cars because all the people already have 1 car. And by that, we're allowing them the freedom of just, not getting another car. These are our 3 cars, and we have one person who's just going to stay at the right to make sure these cars don't get left over. And our blue's the cars now because I switched up the colors by accident. So 5, so we have 3 people, so 3 plus the 3 cars minus 1. We're choosing what the dividers are, and we have 3 minus 1 because one guy is always going to be on the right. So it becomes 5, choose 2, and there are 10 ways to arrange it if everyone got at least 1 car. And stars and bars can be very useful, but again, it's just one way of counting things. And you can understand how to work it if you just understand that you're moving the bars around and whatever's on the left of that person is whatever they're getting, and just make sure there's always one person at the end to make sure there's nothing left over, unless you want stuff left over, in which case you would subtract beforehand.